So today we're going to be solving systems by graphing. Our content objective is students will be able to solve a system of two equations by graphing. Our language objective is students will be able to discuss the differences between a system of one solution, no solution, and infinitely numbers of solutions in terms of the graph of the systems. Why am I learning this? Well, it's important for real-world problems like comparing costs of buying items. So first, let's talk about what is a system of equation. Well, it's a set of equations for which a common solution is found. Hopefully the word a set kind of tells you that there's going to be more than one. So in other words, there's usually two equations. Could there be more? Yes, but in 8th grade, we're just going to be working with two. So the very first thing we're going to be asked to do is determine whether 1, 2 is a solution of the system. So basically, it's asking us 1, 2. If x equals 1 and y equals 2, would this be a solution for both of these equations? Because here we do have a system because we have more than 1, we have 2. So what I'm going to go ahead and do is substitute these values into each equation to see if it leads me with a true statement. So y, I'm going to go ahead and put it, I'm looking at this first equation by the way, I'm going to go ahead and put 2 in for y equals 1 for x plus 1. Does 2 equal 2? Yes, so this one is definitely a solution. Now let's try the next equation. I'm going to go ahead and plug in the same value. So here, 2 times x, which is 1, plus y, which is 2, is supposed to equal 4. So we have 2 times 1, which is 2. 2 plus 2, does that equal 4? Yes, it does. So at this point, since it does work for both, and they must work for both, I can confidently say that 1, 2 is a solution to the system. So just a quick reminder, this ordered pair must work for both in order for it to be a solution for the system. Okay, so let's go ahead and try another example. So it says here, determine whether -3, 2 is the solution to the system. So let's take a look at what the system looks like. So just a friendly reminder, again, for system, there should be at least two equations. I'm going to go ahead and be plugging in x for -3 in for x and 2 for y. So checking the first one, I'm going to go ahead and plug in these values. X is a -3, so -3 plus a y, which is 2, equals -1. -3 plus 2 is -1. Since this is a true statement, okay, this definitely works. Now, I'm going to go ahead and check the second equation to see if it works as well. For y, I'm going to go ahead and plug in a 2, add 3 times x, which is a -3, equals 4. So now I have 2 minus 9 equals 4. 2 minus 9 is -7. Does this equal 4? That is false. This one does not work. So because this this solution doesn't work for the equation, this is not a solution to the system because a solution must work for both. So I'm going to say that -3, 2 is not a solution to the system. Okay, so let's try the next one. Determine whether 20, 40 is a solution to the system. Again, we should at least have 2, and here we have it. I'm going to go ahead and put 20 in for x and 40 in for y. So here we have 20 equals 1/4 times 40 plus 10. Now I'm actually going to change something up. Instead of putting 40 like that, I'm going to go ahead and write it as a fraction. So it's easier for me to cross cancel if possible. I do notice 4 and 40 have 4 in common. So 4 divided by 4 is 1. 40 divided by 4 is 10. So I'm left with 20 equals 10 plus 10. And then that leaves me with 20 equals 20. This is a true statement. So this is going to work. But now, once again, let me try the second one. I'm going to go ahead and do y, which is 40, minus x, which is 20. It's supposed to equal -20. 40 minus 20 is 20. 20 does not equal -20, so I'm going to say this is false again. So unfortunately, since both do not work, I'm going to say that it is not a solution to the system. So once again, I can't stress to you enough, in order for it to be a solution to the system, the ordered pair must work for both equations. So now we're going to go over some background knowledge. Here it says to solve the following equation for y in terms of x. We've never heard it this way, however, you've done this before. Basically, they're asking us to solve for y, and there's an equation in a form that we're used to seeing it to y equals mx plus b. We've done this before where we converted standard form to slope-intercept form, so we technically have solved for y, you're just not used to hearing it in this form. So basically, if they're asking you to solve for y in terms of x, it's basically the same as putting your equation in slope-intercept form because you're isolating y. So let's go ahead and take a look at the first one. So here, in order to isolate y, you're going to have to get rid of the x first by subtracting 2x. And then you're going to get 3y equals negative 2x plus 3. You're going to go ahead and divide both sides by 3, which is going to leave you with y equals negative 2x over 3 plus 9 over 3. So notice each term is being divided by 3. So I'm going to be left with y equals negative 2/3 x plus 3. So hopefully you recognize this. Oh yeah, it looks just like slope-intercept form. So again, if they're asking us to solve for an equation in terms of y, you just need to isolate y. So let's try one more. Here again, we're going to isolate y. So you're going to get rid of the x first by subtracting, leaving it with negative y equals negative 4x plus 11. Now here, be very careful. Some of my students want to stop too early. You still need to get rid of this negative 1. So you're going to divide everything by a negative 1, which is going to end up with y equals, these negatives cancels out, 4x minus 11. Okay. So now I think we're ready to move on to also reminding ourselves how we find x and y intercepts. So here, all you're really doing is if you're trying to find the x-intercept, you want to get rid of y because your focus is on x. The way I get rid of y is by making y 0. So here, if I make y 0, you're going to have 6 times 0 here, which is going to go away. So just solve for x. You're going to get x equals 12. So my x-intercept is 12, 0. Now for the y-intercept, your focus is all on y, so you need to get rid of x. And the way to get rid of x is by making it 0. So here, let's try this again. We're going to go ahead and make this time x 0. So if you make this 0, 2 times 0 is gone. So I'm just left with the negative 6y. So I'm going to divide both sides by negative 6. And I end up with y equals negative 4. So hopefully this looks familiar. This is going to be very helpful for us when we are graphing equations in order to figure out what the solution is. Okay, so now it says here, graph both linear equations on the same coordinate plane. What do you notice? Okay, so for the first one, y equals 2x minus 1. Hopefully you recognize right away that's in slope-intercept form. So I recognize slope is 2 and my y-intercept is 1. We do prefer slope to be written as a fraction because it's so much easier when I'm graphing. So at this point, I'm going to go ahead and graph my y-intercept, which should be on the y-axis at negative 1, which can be found here. Now I'm going to use the slope, which is positive 2 over 1. So I'm going to go rise 2, run 1, rise 2, run 1. And you know me, I always like to go beyond because the more points that I have, the more accurate it's going to be. Now for the second one, okay, I'm actually going to show you 2 methods. I do recognize this is in standard form, but just to get some practice for solving things in terms of y and getting things into slope-intercept form, I'm doing that. I'm going to do that as well. So I'm going to solve for y by subtracting x from both sides, which is going to give me y equals negative x plus 5. I'm going to recognize the slope is negative 1 and the y-intercept is 5. So on my y-intercept, I'm going to go ahead and plot my point at 5. I'm going to use the slope of negative 1, which can be written as negative 1 over 1. So it's going to be down 1 to the right 1, down 1 to the right 1. You keep going until you're done. And there you have it. But like the question says, what do you notice? I hope you recognize that these two lines intersect, and specifically, where do they intersect? They intersect right here, which is 2, 3. This here is the solution to the system. And again, a system means more than one equation. So here, 2, 3 is a solution to the system, which means 2, 3 is going to work for both. So I'm going to show you here. Y is 3, so I'm going to put 3 equals 2 times x, which is 2, minus 1. So 3 equals 4 minus 1, 3 equals 3. This is true. Now let's take a look at the second one, because remember, it has to work for both. So x plus y, so it's just going to be 2 for x, 3 for y. It's supposed to equal 5. 2 plus 3 is 5. 5 does equal 5, so this is also true. So this here proves that this ordered pair is a solution to the system because they are true for both. Okay, so I do want you checking your solutions back into the equations to make sure they actually work. So 2, 3 is the only ordered pair that creates a true statement. If you think about it, why is it only the solution? Because it's the only point in which they intersect. It's the only point they have in common. Okay, so the other thing I wanted to show you was this. Yes, we went ahead and graphed using slope-intercept form for the first equation because it's already in slope-intercept form. The second one's not in slope-intercept form. It's in standard form. So instead of turning this into slope-intercept form, could you have graphed the x and y intercepts? Absolutely. So let's practice that as well. The x-intercept, if I'm looking for that, my focus is on x, so I need to get rid of y. So I'm going to make y 0. So just on top, I'm just going to go ahead and make this a 0, which means it goes away. X equals 5. Fabulous. Okay, now what about the y-intercept? Same idea. If I'm looking for the y-intercept, my focus is on y, and I need to eliminate x by making it 0. So if you make x a 0, basically it goes away. So y equals 5. Well, that's easy. If I put a 5 on the x-intercept, 1, 2, 3, 4, 5, and 5 for the y-intercept, 1, 2, 3, 4, 5. If I draw my line, okay, what do you also recognize? It intersects at the same exact point, 2, 3. So could you also graph using x and y intercepts? Absolutely, especially if something's already in standard form. By the way, standard form, just a friendly reminder, looks like this. It's when ax plus by equals c. Okay, if it's in this form, it's really easy to use the x and y intercepts to figure out what your graph is going to look like. Okay, so now let's take a look at the next one. So here, for the first one, again, just for practice, we're going to go ahead and turn this into slope-intercept form by solving for y. So in order to get y by itself, I'm going to subtract x from both sides, leaving me with y equals negative x minus 1. The slope is negative 1. The y-intercept is negative 1. So starting on negative 1 on my y-intercept, I'm going to go ahead and use a slope of negative 1 over 1. So down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. Keep this pattern up. You can do the opposite by going up 1 over 1, up 1 over 1. And you know I like it. I like for my students to go all the way through, so that way you're as accurate as possible. Second one, also going to convert that into slope-intercept form. I need to isolate y, so I'm going to add x to both sides, leaving me with 2y equals x plus 4. Now I need to get rid of this 2, so I'm going to divide everything by 2, just to show you real quick. And I would end up with y equals 1/2 x plus 2. Now what am I going to do? Well, I recognize my slope is 1/2. My y-intercept is 2. So starting on 2 on my y-intercept, I'm going to go ahead and go up 1 to the right 2, up 1 to the right 2, up 1 to the right 2. Kind of drew my line a little early, but just a friendly reminder, we can do this as far as we can possibly go. Hopefully you can see the intersection here. It occurs at negative 2, 1. So guess what? Our solution is negative 2, 1. But what are you going to do on your homework? You're going to check and make sure it works. So here, I'm going to go ahead and put, so in front of mine, that's x, that's y. So I'm going to get -2 plus 1 equals -1. Oops, let's try that again. -2 plus 1 is -1, so this is true. Let's try the next one. 2 times y, which is 1, minus x, which is -2. Does that equal 4? Well, let's see. 2 times 1 is 2. -2 times, I'm sorry, negative times a negative is a positive, so that's plus 2. Does 4 equal 4? Yes, that is true. So guess what? This solution does work for both. So I'm going to say it absolutely is a solution to the system. But again, this is the only ordered pair because this is the only intersection where both lines meet. That's the only point they have in common. Okay, here it's the same exact problem. The other thing that I want you to realize is, hey, both of them are in standard form. So did I really have to put things in slope-intercept form? No, I could have went ahead and graphed x and y-intercept. So here, using graphing x and y-intercepts, I'm going to go ahead and first look for the x-intercept. My focus is figuring out what the x-intercept is, so I'm going to go ahead and make y 0. That goes away, so x is -1. What about the y-intercept? Here I'm focusing on the y value, so I'm going to just go ahead and get rid of the x value by making it 0. So y equals, whoops, I should put 0 in for x so that I recognize that. So y is a -1. At this point, I'm just going to go ahead and graph on the x-axis. The x-intercept occurs at -1. The y-intercept occurs at -1 as well. Here, you know that I really don't like 2 points. It's usually not that accurate, especially if you're doing it by hand. My open math would make nice lines, but again, by hand, it's not going to be that accurate. So I would want you to use the slope. Here, we're going down 1 over 1, down 1 over 1, down 1 over 1. Continue this pattern. In fact, even do the opposite by up 1, left 1, up 1, left 1. And then you can go ahead and draw your line. Now for the next one, we have another equation in standard form, so I can definitely graph by using x and y intercepts. So the x-intercept here, I'm focused on the x, so I'm going to get rid of the y value by making it 0. So 2 times 0 is 0, so that's gone. -x equals 4, so if you divide by -1 to both sides, I'm going to be left with x equals -4. Now for the y-intercept. My focus is on the y value, so I'm going to go ahead and get rid of x by making x 0. So here, if you make it a 0, it's just gone, leaving you with 2y equals 4. Divide both sides by 2, and I'm left with y equals 2. So here, my x-intercept occurs at -4, so 1, 2, 3, 4. And my y-intercept occurs at 0, 2. Okay, I could continue this on 2, 4, 2, 4. The more points, again, the more accurate your line will be. And then simply draw in your line. I didn't draw it very well. Let's try that again. Much better. So here you can see the intersection occurs at -1. Sorry, that's wrong. -2, comma 1, which is the same exact solution from the previous slide that we did. We just used slope-intercept form instead of graphing the x and y intercepts. Okay, so here they're going to ask us to solve this system by graphing. Now the only thing different about this one, it's actually a little bit more simple. It's just y equals -2, x equals 4. So for y equals -2, I'm going to go ahead and ask you to at least have 3 ordered pairs where y equals -2. So I'm going to go ahead and list 3. Just remember that the y values have to be -2. So here's x, here's y. Does it matter what I pick for y? No, you can pick whatever number you want as long as it fits on your graph. So I'm going to go ahead and graph those points. I recognize I have a horizontal line. And then I'm going to go ahead and do the second equation, which is x equals 4. So again, I just need 3 ordered pairs where x is 4. Does it matter what your y values are? Nope. Pick whatever value you want as long as it fits on your graph. So I'm going to go ahead and plot those 3 points. And I'm going to notice that these two lines also intersect right here, which is 4, -2. You're going to have to check if this works. Okay, so here for y equals -2, what is y? Y is -2. Does -2 equals -2? Yes, that is true. The second equation, x equals 4. Well, x is 4, so does 4 equals 4? This is also true. So I'm going to confidently say 4, -2 is the solution to the system. In fact, it's the only solution because this is the only point in which the lines will intersect. So this will work for both, and this is the only time it will work for both. Okay, so let's go ahead and graph the next one. So for the first equation, I recognize the slope is -1/2, and the y-intercept is at 1. So starting at 1, I'm going to go ahead and go down 1 to right 2. And you know me, I like for it to go completely off the graph. The more ordered pairs, the better. So there's your first line. Second line, if we turn things into slope-intercept form, we're going to solve for y, subtract x from both sides, leaving me with 2y equals -x plus 6. We're not done. We still need to isolate y, so divide both sides by 2. Y equals -1/2 x plus 3. So here, starting with the y-intercept at 3, and using the slope of -1/2, down 1 to the right 2, down 1 to the right 2, and the opposite, up 1 to the left 2, up 1 to the left 2. So here, I would usually determine the solution by figuring out where the two lines intersect. However, these lines don't intersect, okay? So guess what? There is no solution. These lines are parallel, which means they will never intersect. And lines are parallel when the slopes are the same, okay? So there is no ordered pair that creates a true statement in both equations. Now, another way to look at it is we do notice that the slopes are the same, but the y-intercepts are different, meaning they're moving at the same rate, but they're starting at different points. Okay, but once more, I'm also going to show you what you could have done if you graphed using your x and y-intercepts. So the first one is in slope-intercept form, so you're just going to graph your y-intercept, use the slope to graph the line. But for the second one, you could have also recognized, hey, the x-intercept is going to occur at, let's see, y is going to be 0, and x is going to be 6. What about the y-intercept? The y-intercept focuses on y, so I'm going to get rid of x by making it 0. So I'm going to put 0 in for x, it goes away. Solve for y, you get y equals 3. So here, your x-intercept occurs at 6, 1, 2, 3, 4, 5. Ooh, it falls off the graph. Your y-intercept is at 3, 1, 2, 3. So if you draw your line, let's follow this. If you can go 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2. Yeah, it doesn't. Let's try that one more time. Okay, so what I hope you see is, notice I wasn't as accurate with my x and y intercepts. X and y intercepts is definitely going to be really quick and helpful, but there's going to be points in time where you're not going to be able to see if this is truly parallel or not. And we can't always, in the previous example, we were able to compare the slope and say, oh yeah, I can see why the lines are parallel, they have the same slope. Using x and y intercepts, you can't definitely see the slope. Unless you actually calculate it and say, okay, slope, it's rising 1, 2, 3, and then running left 1, 2, 3, 4, 5, 6. So my slope is a negative 3 over 6, which is also negative 1/2. So you can also definitely use that to compare it. Okay, that's going to be a good way to show it if you do choose to use x and y intercepts. Okay, so now what are the 3 possible outcomes? Number 1, it could be one solution, right? The lines intersect at one point. That's one solution. Okay, and then there could be parallel lines that never touch. That is called no solution because the lines will never intersect. And then what about number 3? Well, what if the lines overlap each other? If the lines coincide, that means there are infinitely many solutions because the equations are essentially equivalent, meaning they're the same. So let's go ahead and try number 8 here. I'm going to go ahead and start graphing using slope-intercept form if it's already like that, but if it's in standard form, I'm going to go ahead and graph it using X and Y-intercepts if it's easy. If it's not, I'll go ahead and turn it into slope-intercept form. Okay, so for the first equation, since it's already in slope-intercept form, y is isolated, I'm going to go ahead and figure out the slope is 1/3, the y-intercept is at 2. So I'm going to go ahead and start my y-intercept at 2 and use my slope up 1/3, up 1/3, even go in the opposite direction and draw my line. Now for the second one, since it's in standard form, I'm going to go ahead and graph using X and Y intercepts. So here, I'm going to go ahead and look for the x-intercept. I'm going to go ahead and get rid of y and make it a 0. So here, if you make it a 0, 6 times 0 goes away. Solve for x divided by both sides by 2, leaving me with x equals -6. Now for the y-intercept, again, my focus is on y. I'm trying to get rid of x. I'm going to make it a 0. So here, if I get rid of x is going to become a 0, so 2 times 0 is gone. Divide, in order to solve for y, I'm going to divide both sides by -6, leaving me with here, the negatives cancel out, so y equals 2. So if I graph these two order pairs, I'm going to go ahead and use a different color real quick, and you'll see why. The x-intercept occurs at -6, 0, which is right here. The y-intercept occurs at 0, 2, which is right here. If I wanted to, I can also continue my slope, which is up 1, 2, over to the right 1, 2, 3, 4, 5, 6. So my slope is up 2 over 6, which also reduces to 1/3. So I'm going to go up 1 over 3, up 1 over 3. If I wanted to, I could have also done up 2 over 6. But hopefully you recognize that this is the same exact line. In fact, they're laying right on top of each other. They coincide. So here I would say that there are infinitely many solutions. Okay, how do I know this? Well, my slope is 1/2 for this equation, which is identical to the first equation. My y-intercept also occurs at 2. So notice both of them have the same piece of information. The slopes are the same, the y-intercepts are the same, so that's why it's infinitely many solutions. Okay, so there are infinite numbers of ordered pairs that create a true statement in both equations. Now something I want to clear up is not any ordered pair is going to work. For example, this is not a solution. This point is not a solution. This point's not a solution. The only solutions for this system would be points on the actual graph. So this is a solution, this is a solution, this is a solution. In fact, this is a solution, here is a solution. Even though it's not a nice intersection, it's a solution. This is a solution. This is a solution. As long as it falls on the line, it is a solution to the system. Okay, now for number 9. The first one, since it's already in standard form, let's go ahead and use X and Y intercepts to graph this one. So in order to find the x-intercept, I am going to go ahead and get rid of y by making it a 0. So if I make a 0 for y, this goes away, leaving me with x equals, let's see, divided by -1, it's going to give me a -3. Now for the y-intercept, my focus is on the y. I need to get rid of x, so I'm going to go ahead and make it a 0. So I'm going to go ahead and make this a 0, so this goes away. So if I divide both sides by 2, I'm left with y equals 3/2. Now here is it impossible to go ahead and graph this No, but I'm going to tell you the drawbacks of using this. So here my x-intercept is at -3. My y-intercept is 3/2, which is 1 and 1/2. Okay, here I can't tell this. My slope is not going to be pretty. It's going to be technically 1.5 over 3. Okay, which is 3/2 over 3, which turns into divided by 3 over 1, which is equivalent to 3 over 2 times 1 over 3, which is also 1/2. Okay, so do you want to go through all of this? Maybe not. I would suggest you use x and y intercepts when they're nice integers. But again, is it impossible to use them when they're not in integers? You could definitely use them, but they're not going to be as accurate. So I wouldn't suggest you use this if they don't give you nice integers. So let's go ahead and turn this one into slope-intercept form. For these reasons, I'm going to go ahead and add x to both sides, leaving me with 2y equals x plus 3. We're going to divide both sides by 2, leaving me with y equals 1/2 x plus 3, where my slope is 1/2 and b is 3. So starting on 3, my slope is up 1 over 2, up 1 over 2. Continue this pattern until you have a line. Now graphing the next one. So here, this one's not in slope-intercept form and it's not in standard form. Okay, this is not in standard form because x and y are not on the same side. So just note that. This one would be easy to turn into slope-intercept form because all I would have to do is get rid of the y by dividing by 4, and I'd be left with y equals 1/2 x plus 2. So I'm going to go ahead and recognize the slope is 1/2, b is 2. So graphing my starting point at 2 and using my slope of 1/2, I'm going to go up 1 over 2, up 1 over 2, go the opposite direction as well. And I'm going to notice I have parallel lines. How do I know that they're parallel? Well, because the slopes are the same, okay? But I also notice that these parallel lines will never touch, which means there's going to be no solution. Why is it no solution? It's because they have the same slope, but they start at different points, okay? Okay, enough with this problem. Let's move on. Now, is there a way to tell if there's no solution or an infinitely amount of solutions without graphing? Hint, we kind of already mentioned it, okay? So here, with this video, you're not going to be able to talk it with your partner, so hopefully you start to realize if you end up with the same slope, okay, that means they're moving at the same rate, and you start at the same point, meaning you have the same y-intercept, then you will have infinitely many solutions. Because the lines will be starting at the same point and moving at the same rate, so they will always coincide. Now, if you have the same slope, meaning they're moving at the same rate, however, you have different y-intercepts, meaning they're not starting at the same point. That means they will never catch up to each other, they will never touch, and it would be no solution. Okay, so now let's go ahead and look at one quick word problem. It says here, the Video Club A charges $10 for membership and $3 per movie rental. Video B Club charges $15 for membership and $2 per movie rental. For how many movie rentals will the cost be the same for both video clubs? What is the cost? So how do we solve this type of problem in the past? So first what we're going to have to do is create an equation. So I'm going to say that for Club A, we're going to use y equals 3x plus 10, where X represents the number of movie rentals and Y represents the total cost. Since they do charge $3 per movie and then the $10 for membership, that's why we're just adding 10. For Club B, it's going to be Y equals 2X plus 15 because every movie rental costs $2 and they're charged that $15 membership fee. Now that we have these two equations, we can go ahead and graph it. So in this graph, you can see where these two lines intersect, which is at 5, 25. So that means this 5 is X and this 25 is Y. Since X stands for movies, it means at 5 movies, okay, Y, which is a cost, is going to be $25. So when will they both be the same? Well, at 5 movies. And what will it cost? $25. So since the question was for how many movie rentals will the cost be the same for both clubs, I would say it's for 5 rentals. And what will the cost be? Well, it would cost $25. Okay, and let me show you here, because remember we're supposed to check our answers. If Y is 25 and X is 5, we have here 25 equals 3 times 15, which is 15. Sorry, 3 times 5, which is 15, plus 10. So we end up with 25 equals 25. Now for Club B, same thing. Y is 25 equals 2 times X, which is 5, plus 15. So 25 equals 10 plus 15, and 25 equals 25. So both of them are true, and so I confidently say they will cost the same when there are 5 rentals, and that cost would be $25. So that concludes our lesson for today. Thank you so much for hanging in there with me, and like always, until next time, bye.